Let's look at Taylor's theorem in a slightly different way. Let f of x be a function defined in the interval, closed interval a comma b, such that n minus 1th derivative is continuous on a and b. Okay, closed interval. N minus 1th derivative is differentiable on the open interval a comma b. Then there exists c belonging to a real number in the open interval ab, such that f of b is equal to f of a. That means you can reach f of b by going through these terms, plus b minus a, f prime of a, plus b minus a square by 2 factorial second derivative, plus the nth term would be b minus a. Remember, we are talking of n minus 1. So n minus 1 by n minus 1 factorial n minus 1th derivative, and finally a term for the rest of the. So this would be b minus a n by n factorial f of n c. So this c is what we are talking of. There exists c belonging to the open interval a comma b, such that this summation will give us the f of b. Now let's define a new function, capital F of x be a function on the closed interval a comma b. Now this function would be such that f of x is equal to, now we're going to take this and subtract all the right hand side. So in another way, if you look at it, we are bringing all the right hand side terms to the left hand side here, and we are saying that is this function, right? So f of b minus f of x. Why? Because in here it is f of a, but here we are talking in terms of x, plus b minus x f prime of x, not plus, minus. All the terms will become minus. B minus x f double prime of x by 2 factorial, and so on, and you will have minus b minus x to the power of n minus 1 by n minus 1 factorial times n minus 1th derivative, a times b minus x to the power of n. Now here I have to figure out the a, and I want to figure it out in such a way f of a is equal to f of b. Now why would I put that condition like that? Basically the idea is that here it is given that the nth derivative is continuous, or the terms are continuous till f of n minus 1, n minus 1th derivative, and it is differentiable till n minus 1th term. So that satisfies 2 of Rolle's theorem. If I am able to figure out a such that f of a equal to f of b, then my Rolle's theorem is satisfied, and I would be able to say that f prime of, there is a point f of c such that its derivative, the derivative of f at c is equal to 0. Now the only thing is I have to figure out a. So let's see. f of b is equal to 0. How? Now here instead of x, if I put b, what happens? This is f of b, this becomes f of b. So these two subtracted out goes off 0. B minus b is 0. B minus b is 0. By the way, this should be square. Right? So all the terms will disappear. So you will be left with 0. Since f of b is 0 and we want this condition to be satisfied, therefore f of a is equal to 0. Right? So now Rolle's theorem is satisfied. All three conditions: continuity, differentiability, and f of a equal to f of b. So which implies that there exists a point C in the open interval a comma b such that f prime of C is equal to 0. Now let's see. F of x is equal to, I'm just writing it down from top. Now what we have to figure out is this a. Now we have f prime of c equal to 0. So let's first differentiate this and then we substitute x with c. So f prime of x would be what? Now f of b would be 0. F of x would be f prime of x. Okay, now let's differentiate the next term, this one. Now here this would be chain rule. So minus 1 times f prime of x plus b minus x f double prime. Yes. Now let's differentiate this. This would be again 2 times b minus x times minus 1 f double prime of x plus b minus x square by 2 factorial, here also 2 factorial, f triple prime of x, and so on. And here we need to differentiate b minus x. So this will be n minus 1 b minus x times minus 1 by n minus 1 factorial f n minus 1 x. Remember there is a minus sign here. Okay, then plus b minus x n minus 1 by n minus 1 factorial remains as it is, and this becomes nth derivative of f of x. Okay, and finally minus n a b minus x n minus 1 times minus 1. Okay, now let's simplify this. Let's not write 0 f prime of x plus f prime of x minus b minus x f double prime of x minus into minus plus f b minus x f double prime of x, then comes minus b minus x square by 2 factorial times third derivative of f of x. We'll keep on going, and then we will have minus into minus plus n minus 1 b minus x by n minus 1 factorial f n minus 1 x minus b minus x n minus 1 by n minus 1 factorial times nth derivative of f of x, and finally minus into minus plus nab minus x to the power of n minus 1. And now what's the fun? What happens? This and this gets cancelled, this and this gets cancelled, this would get cancelled with the next term, and this will get cancelled with the previous term. Yes, so what we would be left with is f prime of x is equal to minus b minus x n minus 1 by n minus 1 factorial f nth derivative of x, okay, plus nab minus x n minus 1. Now remember, we are talking of f prime of c equal to 0. Yes, so now let's take care of that. So f prime of c is equal to b minus c n minus 1 by n minus 1 factorial f n of c plus n a b minus c n minus 1 is equal to 0. Let's simplify this. N a b minus c to the power of n minus 1 is equal to b minus c n minus 1 by n minus 1 factorial nth derivative of f of c. Now this and this gets cancelled, so a becomes f nth derivative of c by n minus 1 factorial. Let's bring n to this side, so this becomes f n c by n factorial. So therefore a is equal to nth derivative of f at c by n factorial. Okay, let's put the value of a in the original equation. So what happens? F of b is equal to f of a plus, now we are bringing everything back to the right hand side, b minus a f prime of a by 1 factorial plus b minus a square f second derivative of a by 2 factorial plus, and so on. The nth term would be b minus a n minus 1 by n minus 1 factorial times n minus 1th derivative of f of a plus, now here we do the substitution of a, so b minus a to the power of n by n factorial times f n c. So this is the part where we had a times b minus a to the power of n times f n c. Now that a has been substituted with f of nth derivative of c by n factorial, and this is the Taylor's theorem. Okay, let's play around with this. Let b is equal to a plus theta h. Now here theta is between 0 and 1, open interval 0 and 1, and is a real number. If f of x is such that n minus 1th derivative is continuous on the closed interval a comma a plus h and derivable in the open interval a comma a plus h, then there exists a real number theta belonging to open interval 0 comma 1 such that f of a plus h is equal to, remember this was b, so we have substituted it with a plus h, f of a plus h times f prime of a plus h square of f double prime of a by 2 factorial plus h cube f triple prime of a by 3 factorial and so on, h n minus 1 by n minus 1 factorial times f n minus 1 the derivative of a, and here is where the impact would be h to the power of n by n factorial f nth derivative of a plus theta h. Now let's look at graphic. Okay, now you see this is e to the power of x, so it's a function e to the power of x. Now I remember the expansion 1 plus x square by 2 plus x cube by 6. Okay, this is the first term only, right? Now I am taking first two terms 1 plus x. Now I am using three terms 1 plus x square by 2. Now I am using 1 plus x square by 2 plus x cube by 6. Now I am taking the first 5 terms. So let me remove the initial 4. You see, it's becoming closer and closer to the e to the power of x curve. That is the green curve. So this term actually gives us the remainder part. Remainder to what? Remainder to the perfect matching of the curve. Because of this remainder only, the curve doesn't match. Okay, so now this is called the remainder after n terms in Taylor's theorem. Okay, now let's try something else. Let's say n is equal to 1. What happens in the theorem? Remember, f of b is equal to f of a. Now this is the first term plus, now we use the remainder, that would be what? b minus a by 1 factorial times f prime of c. Okay, now let's bring this a to this side. We get f of b minus f of a divided by b minus a is equal to f prime of c. What's this? This is nothing but the Lagrange mean value theorem. Yes, okay. In Taylor's theorem, we use the closed interval 0 to x rather than a comma b. Yes, so a would be 0 and b would be x, right? So now if we do that, what happens? F of x is equal to f of 0 plus x minus 0, that is x f prime of 0 by 1 factorial plus x minus 0 square, so that is x square by 2 factorial f double prime of 0 and so on, plus x to the power of n minus 1 by n minus 1 factorial times n minus 1 the derivative at 0 plus x to the power of n by n factorial fnc. Now this is what? This is nothing but Maclaurin's theorem. In Taylor's theorem, if you put x equal to if you say a equal to 0 and b equal to x, or rather if you say f of 0, it is Maclaurin's theorem. But here in the previous session we looked at Maclaurin series up to infinity. Now here we are terminating the series at some point. So which means this is with Lagrange remainder. And usually this is, we say R remainder of x is equal to x to the power of this part. X to the power of n by n factorial f prime f nth derivative of c. And here, understand this, the farther you go in the series, the smaller this remainder would be, isn't it? So which means as this goes to, okay, let me not write it like that, as n goes to infinity, r of x goes to 0. Let's solve a problem. Let's say f of x is equal to e to the power of sin x. F prime of x would be what? E to the power of sin x and then the sin x differentiation, that is cos x. F double prime of x is equal to e to the power of sin x cos x times cos x as it is. So here this is the derivative of e to the power of sin x, and cos x is already there. I'll leave it as it is, chain rule. And now I leave the first term as it is and derive. So this is minus sin x. Okay, let's differentiate one more time. This would be what? As I said, this is where the tricky part comes. Now here, this we can write it as cos square x, right? Now let's differentiate this. Sin x, and sin x is cos x, right? Times cos square x. So this will be cos cube x, right? And then we have to differentiate, leave this as it is and differentiate cos square x. So 2 cos x minus sin x. And now we have to differentiate this. So this minus we can bring it out. A to the power of sin x cos x. Let's put this sin x as it is. Then plus e to the power of sin x as it is. And sin x is cos x. Now we need to simplify it a little bit. So e to the power of sin x is common. Cos cube x plus 2 sin x cos x, and this is minus, okay, minus sin x cos x minus cos x, which is equal to e to the power of sin x cos cube x minus 3 sin x cos x minus cos x. Okay, as you noticed, you just take it step by step and do it. Now here in the question it's not mentioned where to stop, right? So let us say we stop at third term. So x to the power of 3, wherever we have cube we stop. Okay, so we stop at this point. So now it doesn't also tell me when, but it does say by Maclaurin's theorem. So the moment it says Maclaurin's theorem, even though we are using Taylor's theorem, it is just a question of putting 0. Yes, x equal to 0. Let's say x equal to 0. F prime of 0 would be what? Remember, f prime of x is e sin x cos x. So e sin 0 cos 0. Sin 0 is 0, e to the power of 0 is 1, cos 0 is 1, so this is 1. F double prime of 0 is what? This is cos square x, let me write it in the right order, e to the power of sin x cos square x minus sin x e to the power of sin x. Now this would be e to the power of 0 cos square 0 minus sin 0 e to the power of 0. This is 1, cos 0 is 1 minus sin 0 is 0, so the whole thing is 0. F third derivative. This is what? Let's do it here itself. Cos 0 is 1, so this is 1, this is 0, this is 1. 1 minus 1 is, this would be 0. Now let's apply the theorem. E to the power of sin x is equal to f of 0 plus x times f of f prime of 0 plus x square f double prime of 0 by 2 factorial plus x cube f triple prime of 0 by 3 factorial and so on. So here this becomes f of 0 is what? E to the power of sin x. So instead of x we have to use 0 plus x times f of 0 is 1. So x plus f double prime of 0 is again 1. So x square by 2 plus this is 0, remember? So this whole thing becomes 0. This sin 0 is 0, e to the power of 0 will be 1. So this will become 1 plus, now it's not very apparent, we actually have to work out the next term to figure out the pattern, right? You do this, you will get x to the power of 4 by 4 factorial times minus 3. Okay, so this would be 1 plus x square by 2 minus, now here 4 times 3 times 2 times 1, right? So this 3 and 3 will get cancelled. So 4 2's 8. So x to the power of 4 by 8. Like this you'll have to work out the terms. But remember, our problem statement says up to x3 and x3 was 0. So we don't have to go up to the 4th power of x. So e to the power of sin x is equal to this. Okay, I think that's enough. Bye for now.